Hello friends, welcome to GT Science tutorial. In this video, I am going to explain about the Born-Lande equation. This is the theoretical method to calculate the value of lattice energy. In my previous video, I have already explained about the experimental method to calculate the value of lattice energy, that is Born-Haber cycle. You can find the link in the description below. So in this video, we are going to understand everything about Born-Lande equation. Both the methods are equally important for your examination. So let's start. Born-Lande equation is the theoretical method to calculate the value of lattice energy. So in this video, we are going to derive the actual Born-Lande equation. To do that, we are going to consider two ions. One is positively charged, that is called cation, and another one is negatively charged, that is called anion. We are considering both the ions to be point charges. So let me write it over here. Let us consider two ions, that is cation and anion as point charges. So as they are point charges, as they are oppositively charged ion, then obviously there will be certain interaction between them. The attraction phenomenon as well as repulsion phenomenon will occur over there. And to derive the Born-Lande equation, we are going to see the effect of both the phenomenons. So first of all, we are going to see the attraction phenomenon, that is the attractive effect between them. Okay, when the ions come together, there will be certain force of attraction between them. Now we have a mathematical expression given by Coulomb which calculates the value of force, and that is given by, let me write it, according to Coulomb's law. We know the mathematical formula F is equal to Q plus Q minus by R square. This is the Coulomb's law. Let us consider this to be equation number 1, where this Q plus is the charge on cation, Q minus is the charge of anion or charge on anion, and R is equal to interionic distance. So this is Coulomb's law. Now let's consider one of the ion is moved towards other. Let's consider anion is moving toward cation. Initially, the distance between them is taken to be infinity because we don't know the actual distance between them right now. But if it moves here, let us consider the displacement made by this anion is dr. Then obviously to move there, it has to do certain work done, right? Let me write it over here. Let the anion moves towards the cation under the influence of electric field. It makes a displacement dr. Then work done in this case, that is dw, work done for displacement dr will be equal to F into dr, right? Work done is equal to force into displacement, and if we put the value, we will get Q plus Q minus by R square into dr. Let us consider this to be question number 2. Now we need to take this anion to certain distance r from this cation. Now we are going to take this anion from infinite distance to a certain distance of r that we can measure from the anion. Then obviously we have to do a lot of work done. That work done can be calculated by integrating this equation, that is equation number 2, under the respective limits. So to get total work done by the anion to reach to a distance r from cation integrating equation 2 under the limit infinity to r. So initially the distance between them was infinity. Now the distance will be r. So total work done W will be equal to integration from infinity to r dw. Let's put the value over here. R dw means this much, right? Q plus Q minus by r square into dr. Now to do the integration, you can see over here Q plus and Q minus are constants. We can write it like this: infinity to r to the power minus 2 into dr. Let's not give any bracket right now. Now let's do the integration. You know very well the formula for integration, that is r to the power minus 2 plus 1 by minus 2 plus 1 from infinity to r, right? This is the actual form that we get by integrating this r to the power minus 2, because there is a formula for integration: x to the power n is equal, and dx will be equal to x to the power n plus 1 by n plus 1. So this minus 2 plus 1 is minus 1, minus 1 will come in front, so it will be minus q plus q minus into 1 by r from infinity to r, and finally it will be minus q plus q minus by r. This is the total work done by that anion to move to a certain distance of r from the cation. Now to do the further calculation, let me erase this portion. I have erased everything and I have written the final expression over here, that is equation number 3. W is equal to, that is total work done, is equal to q plus q minus by r. Now we know this q plus is equal to z plus into e, and this q minus is equal to z minus into e. Then W will be written as z plus z minus e square by r. This is equation number 4 now, where this z plus is the total number of charge, or number of charge on cation, and this z minus is the number of charge on anion, right? Number of charge on cation and number of charge on anion, and this E is the electronic charge, whose value is 1.6 into 10 to the power minus 19 coulomb, that we know already. So yes, this is the expression that we get. This is equation number 4. Now we know that as we are talking about attraction, then obviously there will be some other factors that affect this phenomenon as well. So the attraction of the ions is affected by two factors. They are number of ions and the geometry of ionic compound. So that attraction energy total work done, that is also called attraction energy EA, will be affected by two different factors, and one of them is number of ions and another one is the geometry of the ionic compound. So this total work done is itself called the energy, okay, attraction energy. So attraction energy will be equal to, we are going to multiply this equation number 4, the right side of equation number 4, by two different constant. One of them represents the number of ions and another represents the geometry of the ionic compound. They are, sorry, there should be minus over here, okay, I forgot minus, and A into A, Z plus Z minus E square by R. So here this Na is the Avogadro's number. Avogadro's number. Its value is 6.023 into 10 to the power 23. This represents the number of ions, and this A, capital A, is called Madelung constant. In some books it is represented by M, but I have written A because in my book it was represented by A. So A is equal to Madelung constant, and it can be it entirely depends on the coordination number of the ionic compound. So particular value of particular value of coordination number will have particular value of Madelung constant. So this is the total attraction energy, that is equation number 5 over here. Now as the point charges come together, that is as the ions come together, not only attraction but there will be repulsion as well. Now repulsion will happen between the nucleus of the two ions and the electronic cloud between them. That means there will be nucleus, and that is always positively charged for everything. They will try to repel each other, right? Not only that, they have electronic cloud, and they will try to repel each other as well. So Born and Land derived a formula that depends on the interionic distance, that is R, and different constant that gives the total energy of the repulsion. So according to Born and Land, the total repulsive energy is given by ER is the repulsive energy, and it is given by the formula B by R to the power N. This is equation number 6, where this B, capital B, is called it is a constant. It is a constant called Born coefficient that depends on the coordination number. And similarly this N, it is also a constant called Born exponent, and that depends, that is a 9-digit number. This is a huge number, and it can be calculated theoretically as well. So it can be calculated theoretically, and we can put the value over here to find the value of ER, that is the repulsive energy. Now let me erase this portion. So we now have the formula of attractive energy as well as repulsive energy. So when the point charges come very close to each other, there will be both of this energy between them. So total energy can be calculated over there. So total energy is the sum of EA and ER. Total energy is the algebraic sum of both the energies. So E will be equal to EA plus ER. Let's put the values over here. In place of EA, we need to put minus and A into A, Z plus Z minus E square by R, plus in place of ER, we need to put B by R to the power N. Let me erase this portion now. You are taking the screenshots of this derivation, and you are understanding everything properly. So this is equation number 7 now, right? So this total energy E is equal to the lattice energy of the system. So this E can be written as U. U is lattice energy, we know very well, right? Lattice energy is represented by U, and in some books it is represented by LE as well. This is a negative value, completely negative value, and this is the lattice energy. Now as we got the lattice energy value, you might be thinking that the derivation is completed, but no, the derivation is not completed. We still need to find the value of this B. By finding the value of B, we need to put the value again in this equation so that we can find the final answer, that is final expression of this U. Now to do that, we are going to use the boundary condition. To understand boundary condition, look at here. This is cation, this is anion. they are coming towards each other, right? Or the anion is coming towards cation, then the interionic distance will keep interionic distance will keep on decreasing. So there will be attraction as well as repulsion simultaneously. So at certain distance RO, that is at equilibrium distance, that is also called equilibrium distance, the attractive force and repulsive force will balance each other. Attractive energy and repulsive energy will be equal. That is called the equilibrium distance, and that is represented by RO. At that condition, the change in internal energy, the change in total energy, that is this U, lattice energy, will be 0. So at R is equal to RO, the change in this lattice energy with respect to this distance will be equal to 0. So we are going to use this boundary condition to find the value of B. For that, we need to differentiate this expression. Now for that, what we will do, we will directly write it like this: du by dr naught dro will be equal to, we are going to replace this r, all the r over here, by ro. So what we will get? Na minus Na and sorry, and not this should be a z plus z minus e square. These all will behave as constant, and it will be d by dro ro minus 1. This r will go up and its power sign will change, plus similarly it will be written as b d by dro into r to the power minus n. This is how much we get. Now if we apply this condition over here, then we need to write 0 is equal to, this will be minus na a z plus z minus e square. Now we need to differentiate it. Now to differentiate it, what do we need to do? This minus 1 will come in front, and ro's power will decrease by 1. Similarly, we'll do the same thing over here. B is over here. This minus n will come over here, and similarly we can write ro minus n minus 1, right? We get this much. We can further write it like this: minus minus will give us plus. So na into a z plus z minus e square by ro square. We get this much. Minus plus minus will be minus bn by ro n plus 1. If it comes down in the denominator, then the power sign will change, and sign is negative over here, it will be positive now. One sign is negative over here, it will be positive now. That is the law of indices, right? Now to find the value of B, that is Born coefficient, we need to take this B's value to other side, and in the left side as there is 0, so we can do like this: B by ro n plus 1 will be equal to na into a z plus z minus e square by ro square, right? Sorry, there will be an as well. Therefore B will be equal to this value, this denominator value will come this side and it will be in the numerator, then this n will come in the denominator. So we'll get na into a z plus z minus e square into ro n plus 1 divided by n into ro2. So this is the value of B. Now we are going to replace the B from equation number 8 by this value. So then equation 8 becomes, look at here, this equation 8 will become u is equal to, we need to write this value minus na into a z plus z minus e square by r. In place of B, we need to write this value plus na into a z plus z minus e square into r naught n plus 1 divided by n, there is this n into ro square into this r to the power n will be over here as well. Now let's do a simple calculation over here. What is common among them? Just take the common, okay? This will be ro as well, and a dot a z plus z minus e square. These all things will be common, right? By ro. Let's do the calculation first, then we will take the common, okay? And a into a z plus z minus e square by n into ro's 2 plus n. This will come down minus n minus 1. This is how much we get, right? minus n minus 1. So it will be 2 plus 1, so 2 plus n. So n and n will get cancelled out, and we will finally get minus na dot a z plus z minus e square by rho plus na into a z plus z minus e square by n into rho. So you have to be very much careful while doing this calculation. Okay, most of the students make mistake over here. This calculation is little bit time consuming, and you have to be very much careful. Don't write anything wrong. Okay, you can take 1 or 2 minutes extra or even more than that, but don't do wrong. Now among them, can we take something common? Let me read this portion. Is anything common over there? Yes, you are thinking correct. U is equal to something is common, that is minus na dot a z plus z minus e square by rho is common, and in the left side there will be 1. In the right side this minus plus will be minus, and 1 by n will be remaining over here. This is the Born-Lande equation. This is the Born-Lande equation, and in SI unit the value of this u will be equal to minus na a z plus z minus e square by 4 pi epsilon naught into rho 1 minus 1 by n. This is the final expression of the Born-Lande equation, where this epsilon naught is equal to permittivity of vacuum, and this let's consider this equation to be equation number A. Equation A is the Born-Lande equation. Now, as we understand the Born-Lande equation, let's see the application of this equation. Let's see a numerical problem that is very important from this part, and that numerical problem will help us to understand the use of this Born-Lande equation even more. So let me erase this portion and let me write the question. And if you haven't if you haven't taken the screenshot, you can take it now. Okay, I'm erasing this portion now. So I've already written the question over here. Look at here. Calculate the lattice energy of sodium chloride using the Born-Lande equation. And the given conditions are over here. The value of A, that is the Madelung constant, is given this much. Z plus, Z minus over here. E, that is electronic charge. Epsilon naught, that is permittivity of vacuum. And NO, let's consider this. And A is the Avogadro's number, pi. RO means the equilibrium distance, and is the Born exponent value. So these are the given values, and we are going to calculate the value of the lattice energy by using the Born-Lande equation. So we have a formula, we just derived that right now. Since U is equal to, what is the formula? Try to remember it. Minus Na into A Z plus Z minus E square by 4 pi epsilon naught Rho into 1 minus 1 by n. This is the formula, right? So let's put the values over here. There is minus Na means it is given over here, Na 6.023 into 10 to the power 23 into A is given to be this much, 1.74756 into Z plus is given to be 1, Z minus 1 into this E is given to be 1.60281 into 10 to the power minus 19 whole square divided by 4 into pi. Pi is given to be 3.14159 into 4 pi epsilon naught. Epsilon naught is given to be 8.854188 into 10 to the power minus 12 into this R naught is given, Rho is given to be 2.814 into 10 to the power minus 10, and there is 1 minus 1 by n. N is further given to be how much? 8. So this is the form that we get after putting the value in the Born-Lande equation. And if we put the value in calculator, then you will directly get minus 755 kilojoule per mole. So this is the value of lattice energy that we get by putting the value of the putting these values in calculator. So I hope you understood this numerical problem as well. So in this video we understood the Born-Lande equation, and we saw a numerical problem this type of numerical problem is frequently asked in examination as well. So I hope you know how to do it. And as I've already told you, this is the theoretical method to calculate the value of lattice energy. In my previous video, I have already explained about the experimental method. There is no any big difference between those two methods. The values are almost similar. That's why Born-Lande equation is also very important for our calculation of the lattice energy. So that's all in this video. If you like the video, please share this video as much as you can, and thank you for watching the video.